Greetings, everyone. It's good to have you here with us. And again, we apologize for having to change the date of the workshop. Instead of the third Saturday, we're coming to you on the second Saturday, and we know that that has caused some scheduling problems for some people wanting to be in with us. Actually, both Dr. Jake and I will be on airplanes next week at this time. He is going to Jeddah, Saudi Arabia, to do some visits there, and I'll be going to Riyadh, Saudi Arabia, to do some visits in that area, and then we will go together to Armenia. So if we had been in hotel rooms already, we could do the workshop from there, which we have done before, but we're not able to do it. So thank you for those of you who are able to change your schedules and be with us today. We have what I consider to be a very extremely important workshop today, and that's about the teaching of mathematics, and we'll get into that in just a minute. But welcome, and we're happy to have you here, and our format will be pretty much the same as usual. So let me turn it over to Dr. Jake, who will give some announcements and some other things going on at Array Global.
Thank you, Dr. Ray. It's great to be with everyone. It's beautiful where I'm at. It's finally getting warm and it's turning into spring. So we're grateful that we could be here on this Saturday for an hour and listen to this presentation about mathematics. We're excited about that. We've had a lot of people ask about mathematics. So we're excited about having Mr. Hill with us today. A few different announcements that we want to make sure that you're aware of. We have 2 more weeks before the Stella Science Fair closes. It closes May 1st. So please get your students into and submit their entries for the Stella Science Fair. Last year, Dr. Ray, I believe we had almost 1,000 people, part of our students that were part of that. And we had some outstanding videos. This is the 4th year that we're doing it. So we hope that everyone gets their students involved. It's a great way to get them involved in something so academically based and to interact and see what other students are doing from around the world. We also have Me and My Community that we do every single year, and this is to promote students to do service projects in their communities and give back. If your student does 20 hours of community service, we will give them a certificate. We have an awards assembly, and they can put that on their application to colleges, universities, and things like that. We'd also like to remind everyone next month, we will be back on our regular schedule for our workshop. It'll be the 3rd Saturday of the month. It'll be May 18th, and it will be yours truly who will be presenting. Dr. Ray, myself, and Dr. Mike Poe will be with us also, and it will be a forum. You'll be able to submit questions to us beforehand, and we will be able to answer those and talk about some of the best educational practices that are going on currently. We'd also like to remind everyone about our Student of the Month. And if you're an Array Global School, you can apply for Institution of the Month. We just like to highlight some great things that are going on and give other schools, educators, students some ideas of some awesome things that are going on in the world. Also, we'd like to make sure that you're aware of our Array Global Educators Association. It's a closed Facebook group that you can post questions to us. Dr. Mike does a great job in answering questions and leading that discussion. And you can answer some of those questions yourself. It doesn't have to be us answering all those questions. So at the end of this workshop, we will post a survey in the chat, and we'll give you a few minutes to fill that out. Please fill that out, even if you're watching us on Facebook on our live stream, or if you're watching us on Zoom. Make sure you fill that out in its entirety. We're requiring everyone to post a few different items that they learned and they took away from the workshop. So as Mr. Hill is presenting in just a few minutes, make sure you're writing a few different things down that you can implement specifically into your classroom. Even though the workshop's on mathematics, instructional practices are going to be talked about here that you can implement into your classroom and help each one of your students be successful. So, Dr. Ray, did I miss any announcements?
I don't think so, but I encourage you all to do what Dr. Jake mentioned. Send us your questions or things you would like us to discuss at the May workshop. It's really your opportunity to deal with issues that you find maybe we've covered it in a workshop, maybe we haven't. and we would be most pleased to use that. In fact, if you don't have any questions, we might just sit and look at each other for an hour. So we'll depend on you to get some questions to us. I wanted to take this opportunity to introduce Mr. Cary Hill. The thing that most of you will probably really appreciate, he's currently doing what you're all doing. He's a middle school math teacher, and he's dealing with this on a daily basis. And so the issues that he will share with us and the ideas that he will share with us today, if you get a recording of this workshop or you get the PowerPoint that you'll have access to at the end, please be sure to to show it to your staff, because the concepts are universal for the teaching of mathematics, but also universal for generally good teaching practices. So, Cary Hill, it's good to have you with us, and the show is yours. You're on, and we're excited to hear what you have to say to us.
Thank you. Well, greetings this morning. Let me take a minute and get my screen shared here so then we can start our presentation. All right, this morning I really want to just focus on this idea of teaching math conceptually. And this idea was born out of in Idaho several years ago, where I teach. There was a big focus called the Mathematical Thinking Initiative, and that was a class I took, and we discussed some of these ideas, and that's where these ideas really started to kind of marinate in my mind a little bit, and where I really began to think about how I could implement some of these ideas in my classroom on a more regular basis. So a little bit of background about me. I was born and raised in Idaho near Nampa and Boise, and that's also where I currently live and teach in this area as well. I do have a bachelor's degree and master's degree from Northwest Nazarene University. I've taught for 27 years in secondary math, anywhere from algebra to geometry, and even dabbled in AP statistics for a few years, and that was really fun. We've lived mostly in Idaho and taught here, but we did also have the opportunity to teach overseas in South Korea at an international school, and that was a very rich experience, and just learned a lot and got to experience the International Baccalaureate curriculum and program, and that was just a great experience for me personally and professionally, and for our family. I do currently teach Algebra 1 and Algebra 2 to students in 8th and 9th grade at North Junior High in Boise, equivalent of middle school, and in most other places. And then I also have served as an adjunct instructor for the Teaching Math in the Secondary School. Basically, they call it the Secondary Math Methods course at NNU. I've done that for the past 10 years, and I love working with pre-service teachers and giving them a good foundation to build on as they move into their student teaching and into their first experiences out in the classroom. So with that, as I said, the main idea I want to focus on today is this idea of building conceptual understanding in math. And these ideas are in large part to a man named Jerome Bruner. He came up with these 3 stages of cognitive development, and representing new learning, how our brain kind of adapts and gets ready to learn new things and then processes that, and you move kind of from different level to different level. It's just also interesting. My wife just mentioned the other day that she read something about Jerome Bruner. He was actually born blind. He was not able to see when he was born, and then maybe around year 2 years old, he had cataracts removed and was able to see. I think that's kind of interesting, thinking about these stages I'll be talking about. I wonder if even that early impact of not being able to see maybe had some impact on him thinking about these different stages I'm going to talk about. The 3 stages, and you may or may not have heard of these before, but it's what we call the inactive kind of representation or inactive stage, the iconic stage, and the symbolic stage. And really, this could apply not just to math. This applies in so many areas of life and just learning inside the classroom and outside of the classroom. But as you can kind of see, if you think about kind of the roots of some of these words, the inactive part of it is very active. Maybe we get our hands on something, we stand up, we act something out. And that's how we maybe first encounter something new and help it really start to get into our bones a little bit, so to speak, as we actually play it out with our bodies. And then after that, sometimes it's great to be able to do that, but that is not always the most efficient way maybe to do something in math, or we maybe don't have all those tools all the time. And so sometimes after we've experienced an active representation or approach something inactively, you might want to move on and think about the iconic representation, which, as you can kind of see here, is focused on the word icon, a picture of some sort. Okay, and you can see in this case, you see at first there were some cubes there, some physical cubes that somebody might hold. The second one is some pictures and drawings of some cubes, more on a two-dimensional surface. And then after we've experienced something maybe iconically, then that is a good time, after we have a really good foundation and actively and iconically, then to start throwing in the symbols of stuff. And hopefully you see how this ties into math. If I just threw that last expression up on the board for students, it may not have a lot of meaning for them if we hadn't built some understanding in these other areas beforehand, the inactive and the iconic. So you have inactive, iconic, and then symbolic. And usually the idea is to kind of move through these stages in that order. And it might be in one lesson that you do that. It might be over the course of several days. Maybe one day is an active, the next day you take an iconic approach, the next day you take a symbolic, or maybe it's within a whole unit that you start the unit kind of inactive, and then towards the middle you move towards iconic, and then maybe towards the end of the unit you're developing maybe those algorithms and those processes that really rely on the symbolic representation of whatever it is you're trying to teach. So I just have several examples today and ideas that I want to share with you about how you could maybe incorporate these ideas in your classroom. And at the end, then I just have a few kind of bonus things that I've kind of used over the last several years that I just have found really successful with my students. So this is kind of a handout, and this presentation will be made available to you through Dr. Frankum. And so this is just a handout I actually use in my math methods class just to help students get an idea. So maybe we're dealing with transformations, rotation, reflection, etc. The inactive part might be using what I call mirrors, that little red plastic looking thing, or tracing paper to get kind of an active visual way to see what's going on with transformations. And then we might move to a table or to a graph to experience the transformations that way and see what patterns we might notice. And then out of that, we might be able to make more of a symbolic representation as we write those transformations as functions. Okay. The next one is about integers, and I'll unpack that a little bit more because I have some slides that we're going to be doing on that. You see one here. The top one is kind of a row of fraction, kind of moving from inactive to iconic to symbolic. Some algebra tiles, and I'll mention both of those coming up. And then also with functions, and I'll mention that example. So that's kind of a big overview of some of these ideas and how they might play out in some different areas of math. In elementary school, one of the main inactive tools that a teacher might use are base 10 blocks, okay? And it's such a great way to build kind of a good foundation in our number system and place value and ones place, tens place, hundreds place, thousands place, and so on. So I'm not going to spend a lot of time on that, but I just wanted to mention that. And there are some great online manipulatives. Inactive is great, but if you don't actually have the tools in your classroom with technology, there are ways to at least model that on the screen at least. And so I put a link here, links in there, and you can drag different amounts in, and especially for like things like subtracting and borrowing or regrouping for subtraction, I think base 10 block can be really, really powerful, or for adding and like carrying over into the next column. It just really, really can be helpful. So I don't want to spend a lot of time there, but the one I want to spend a little more time on here as we start is kind of this idea of using charged particles kind of for addition of integers. And in my classroom, I just have these little kind of 2-color counters that on one side are red and one side are yellow. And so we can represent the positive maybe as the yellow and then the red as the negative. And students can actually physically manipulate these and move them on their desk. And we learned really quickly that, oh, one positive and one negative should cancel each other out. And we call that a zero pair. then we can start actually looking at doing, math problems. Okay, so I'd ask students what they see in this picture right now. They see 5 positives and 4 positives. And this at this stage, when I'm introducing this, it'd be in the middle, at the middle school level. So they would have been adding 5 plus 4 for lots of time, lots of years already. But I might start here just to get an idea. Okay, it's a positive plus a positive. It's going to be more positive. It's going to be 9. And then we might think about, oh, what if I have a group of negatives, 3 negatives and 5 negatives, and we lump all those together, and hopefully they see it. Oh yeah, if we just pile them all together, we're going to get 8 negatives. Okay. Where I think it really gets helpful with using these charged particles is when we do start running into, different signs. Okay, we have a positive 6 on the left, we have a negative 4 on the right. And I would actually encourage students with their chips on their desk to actually move them around and maybe pair them up. For the sake of today, I'll just do this, and I'll kind of maybe circle the pairs that go together. Here's a 0 pair that cancels out. Here's a 0 pair. Here's a 0 pair. And here's a 0 pair. And so then they can see, oh yeah, if it's 6 positives plus 4 negatives, what's going to be left over? Well, more positives. Okay, so it has to be a positive 2 as our answer. And that's what we want to focus on. What's left over? A positive 2. Same idea with addition still, but now we have less positives and more negatives. 3 plus negative 7. And so again, as they match those up, they would be able to pair them up and see what's left over. And in the end, they really hopefully start seeing, oh, it's really kind of like a subtraction problem because you're just taking away pairs from this. How many more negatives are there than positives? Well, there's 4 of them. Okay? And just seeing that visual picture, or again, doing that physical enactment of moving those chips around on their desk can really, I think, help students and help them internalize what's going on and see the visual background of why we do what we do with signed numbers, positives and negatives. And then comes subtraction, and that always gets a little interesting, and especially when you're subtracting negatives and things like that. So could we still use that when it gets to even more, some of the tougher ideas? I think we can. Okay, so on this one, I wanted to just do 9 minus 4, and again, it's one they've been doing probably for a long time, but basically you could just go through and just cross stuff out. I have 9 positives, I'm subtracting 4 of those away and just getting rid of them. And so you can see, yeah, cancel, cancel, cancel. All we have left is these 5. And so our answer does make sense to be 5. But I also think it's a good idea, good time to introduce and bring in the number line, which is more of an iconic idea. So we have this kind of more inactive, physical thing with the chips. But the number line can also be really powerful. And I always have a number line in my classroom that I can point to and refer to and put magnets on and things like that. And so as I think about subtracting, we could kind of approach it in 2 ways with number line. We could say I'm starting at 9, and then I'm going down 4 units, okay? And where do we land? We land at 5. So that's one way to approach subtraction on the number line, and that can be helpful. But another way I also like to think of our way to think about subtraction. Let me erase that. Okay, the other way we could think of this is really think about distance. The distance between, or the difference between 9 and 4 on the number line. So locate 9, locate 4. And when I'm subtracting, another way to think of it is I'm finding that difference or distance. And sure enough, there are 5 spaces in between there. And that will really come into play when we're subtracting with negatives for sure. So then what about one like this? Okay, so as I look at this, there's a big group of things here, and we have to kind of already think about maybe pairing some things up. The overall charge right now is a negative, okay? And I'm taking away 2 of the positives is really what it's saying. Okay, I have a negative 6 charge and I'm subtracting 2. And so again, visually and physically, what would happen is we could take and cross out 2 of these negatives. Or sorry, 2 of the positives. So I could take that away. That's subtracting 1. This is subtracting 2. And now as I think about it, now instead of having negative 6 as my overall charge, if I pair these up, well, now I have 1, 2, 3, 4, 5, 6, 7. I have 8 negatives. So when I do start at negative 6, again, this is a nice time to tie in the number line. if I start at -6 and I'm subtracting, I could think of anytime I'm subtracting, I'm moving down the number line. And I'm, in this case, again, landing at -8. So giving kids that visual of what's going on with the number line and with these charged particles. So then what about this? Here's -4, and I'm supposed to subtract 6. Well, what if I don't have 6 to subtract? Well, you can always throw in a 0 pair. That doesn't change the value. It's still a -4 overall. This is still a -4 overall charge. It's just I have more stuff going on. So I'm adding 6 0 pairs in this case. Okay, and then at that point, we could start going through and kind of thinking about taking away 6 positives. If I take away 6 of the positives, well, there's going to be a lot less positives going on in here. In fact, all the positives are going to be gone. So if I start at -4 and I subtract 6, I really have a whole bunch more negatives. I will really have 10 negatives going on in our picture. Okay, so hopefully that's giving you an idea with the charged particles, but then I want to just land with as far as the subtraction with, what about if I'm subtracting negatives? Well, again, in this picture, the problem is there's 6 positives, but I don't have any negatives to subtract. So I might go ahead and bring up a couple 0 pairs, and then we can physically see that if we take away those 2 negatives that are sitting there, well, then there's going to be no negatives left. I'm taking that negative away. I'm taking this negative away. And so now I really just have +8. So then hopefully kids can even we can kind of bring kids to the conclusion that, oh, when I'm subtracting negatives, what is that really the same as? It's really the same as doing 6 plus 2. And so that brings in that idea of, oh yeah, whenever we're subtracting a negative, it really turns into that plus a positive. The other place that, especially on this one, I think what we can do with the number line for kids that's helpful is this. Sometimes I've heard people say, oh yeah, we're starting at 6 and I was supposed to subtract -2, but that double negative turns me around, and you can do some different things with that. But I think an even more powerful way to do it is just, again, getting back to that idea of distance on the number line. How far is it from 6 over here to -2? Well, what's the total distance? There's 6 on the positive side, but there's also 2 on the negative side. What really ends up happening is we add that positive distance with that kind of negative pointing distance, and that gives us a total distance of 8. So again, seeing that visual picture hopefully will help students. And then again, if you already had -8, and you were subtracting -3, this one, we wouldn't have to add anything in there. We could just start crossing stuff out. So if you started way down at -8, and again, you're getting rid of negatives, it's going to be less negative in the end. Get rid of, get rid of, get rid of. All we're going to have is -5 left there. Again, you could also think about kind of distance between, how far is it between -8 and -3, and you could kind of look at that distance, and it's 5 spaces, but because of kind of the way we're going with it, it's the 5 negatives left over. So I think that one really helps with the charge particles and the 2 color counters. You can do multiplying really easily. Here's 4 groups of 3 positives. Oh yeah, 4 times 3 is 12, but then turn them to negatives. 3 groups of 5 negatives, sure enough, -15, a negative, a negative, a negative. So it brings in that idea of, what if we're multiplying a positive times a negative? It's going to be negative. Okay? And then you get back into the negative times negative being a positive and all of that. Then multiplying on the number line is also really helpful. Just these repeated jumps, that's what multiplication is. There's repeated addition. 2 plus 2 plus 2 plus 2, or in the bottom one, -2 plus -2 plus -2, and so on. So that's what I wanted to kind of talk about with the 2 color counters and integers. And again, here's some options for you. There's this didax.com that has 2 color counters that you can just drag. Kids can drag around and play with them. I liked this one. This is a Math's bot, and I liked it because it actually would bring up problems that students could actually then model. It would give them a problem to try and do. And you can do some different things. You can flip different things. A new example, for instance, I think that's what I tried yesterday and it worked, but it's not coming up. Anyway, you could drag these out here and just see some different things. You can flip things over, change them and everything. Anyway, so it's fun to play around with options online, especially if you didn't have some of those things available in your classroom at that point. So another big area that I think that kids struggle with is fractions. Even as they get into my 9th grade class or 8th grade class, sometimes they don't have a good foundation of what fractions mean. And especially in the last couple of years, I've had some kids say, well, I was in 4th or 5th grade during COVID and I didn't get a good foundation in fraction. I missed fractions. And so I don't have a good picture of that. So even in my 8th and 9th grade class, sometimes I need to draw a picture for them. So here's some fraction strips that are kind of fun to deal with. And there's fraction circles on the other one as an example. Actually, on this one, I just made the link so you could see here's a number of different kind of online manipulatives, unifix cubes, number lines. You got the 2-color counters, a bunch of different base 10 blocks here too. So here's the fraction kind of strips or tiles. Maybe it's going to load. We'll see. Okay, well, since that is not loading, I'll just, what I did on this one is I just dragged these different tiles out. It was kind of neat to be able to see what fractions would add up to equal different things. And I also especially liked this version because it had a number line you could put up there. So I could easily model, like on this picture, what 2/3 plus 1/2 turns out to be. But it should end up being 1 and 1/6. And again, that's the visual picture. But then you could start unpacking, what we do with the denominators and getting a common denominator and all of those things and how that ends up making sense of the answer that we end up getting. Just some other visual pictures with fractions. Of course, food always comes into play with fractions, it seems like pizza, or you're gonna see a chocolate bar or anything like that. So in this case, we're asking students to identify what the fractions are, like 1/3 plus 1/5. And then, okay, we can't really add those pizzas together because they're different sizes. And so it's hard to know what that is if I shove them into the same pan. And so it brings up this idea of, oh, what if we just cut them into smaller pieces so they're identical sizes? And in this case, that brings up the idea of a common denominator of using a 15. So 1/3 is really the same as 5/15. 1/5 is the same as 3/15. And you can go into all the, all the processes and algorithms of getting that common denominator and multiplying by a 1 and all of that with students. So just bringing in that visual picture for students.
So
I like this.
Mr. Cary, I had a quick question.
Sure.
Can I interrupt?
Mm-hmm.
Yeah. So when do you go from like manipulatives to actually like some of the drawings that you're showing and some of the images?
Yeah, that's really good.
Well,
partly.
Yeah, kids love playing with things, and kids can visualize
playing with stuff.
Yeah.
But if you only played with the stuff all day, you'd never get anything done, right?
That's true.
Playing with it so much, right? But no, you're right. I mean, it's not efficient. And are they always going to have these available to them when they're out doing these different mathematical operations? No. But they can always take them with them in their brains because you've identified and helped them kind of attach it to something that means something to them, and it's that conceptual idea for them. So so that's the idea of moving from the inactive and then moving on to something that maybe they could sketch out or draw, which again is still a little bit visual. But then the point is, even on this diagram, I'm not going to have them always do the diagram. My goal is to be able to have them add 1/2 plus 2/5 without the diagram, knowing how to get a common denominator and things. But this just helps them understand why we have to do what we do. So not just memorizing a process, but they're understanding why we do the process, I guess. Does that answer your question?
Yeah, I think so. And since you're talking mainly about middle school and junior high level students, they've probably already used the manipulatives when they were in elementary school in the lower grades. So they can actually, they understand that and they have that concept in their mind. And now they can visualize it when they see it on paper or on a computer program.
Yes. Yeah, hopefully. Yeah. This example came from Common Core Sheets, which when I was working on developing a class for some kids that were struggling learners at the 8th and 9th grade level. And so I was just looking for practice sheets and just examples and stuff like that. And I really liked this idea of using these little squares. And so I see 1/2 on the left and 2/5 on the right. But it's very easy on the right one if I just draw the line across like I see it on the left. And if I draw the lines down vertical on the first one, I can actually turn that 1/2 into tenths very easily and see it's 5/10. I can turn the 2/5 into 4/10 very easily. And we can see then all together, we really do have 9/10 if we were to shove all these into one big picture. So anyway, Common Core Sheets, I put that link there. They have lots of visual fraction things. So you'll have that available when you have the PowerPoint. This was just a subtraction with chocolate. Hershey's chocolate has 12 little squares conveniently, or 12 little rectangle pieces. And so it's easy to break that up into 12ths and think about subtracting half and that kind of thing. So I'll spend a lot more time on some of the adding, subtracting. I think you're kind of seeing hopefully the ideas there. I want to get into just multiplying and dividing a little bit. I think it's helpful for students to see, again, maybe on a number line with multiplying with fractions and doing kind of those jumps like I was showing. If I'm doing 1/3 times 6, why do we do what we do with that? Well, again, here's a third jump. Oops, let me get this. So with these third jumps, we could say, oh, here's a third, that's 1/3. Well, there's another third, there's another third. That's 3/3 so far, and obviously that lands us at 1. But again, if you do 6 of those jumps, where does 1/3 times 6 land us? It does land us at 2. And so if they see, oh yeah, that kind of starts establishing that idea for multiplying with fractions, that looks like that top number just gets multiplied by the top number. The numerators get multiplied, and then the denominators get multiplied. You can do the same with that bottom one where it doesn't maybe land on a whole spot. You can kind of see where it lands and even develop kind of the idea of mixed numbers and things from that. But I'd also really like this idea for multiplication, kind of that box model again, and thinking of the idea of 2/3. And on this one, I want to really think about how far across 2/3 is. Think of this as a 1 by 1 square. Maybe it's a 1 meter by 1 meter, or whatever unit you want by whatever other unit. And so that's 2/3 of the way across that unit. Okay? And this is 3/4 of the way going up. So if I multiply 2/3 times 3/4, I'm really interested in this area right here. And sometimes it actually is fun to do this with highlighters. If I can find that highlighting toolbar. A little bit smaller. There we go. Okay, I'll make this a little bit smaller so I can see this. Anyway, so I can highlight maybe the 2/3. We'll do yellow and green. So I can kind of highlight that one in yellow. That's 2/3 of the whole box. And then the other one is do 3/4, and I'll highlight this. But what you start to see is, and kids can do this with colored pencils, and again, it brings kind of that very visual, but also a little bit of an active, because they're kind of coloring it. And they see that, oh yeah, what is left over if I multiply a 2/3 times 3/4? What am I really focusing on is this area right here, which is 6 pieces out of 12 total pieces. And oh yeah, that's why we get 1/2. And then when we have them start, thinking, oh, okay, yeah, I did get 6 pieces there altogether. Or 6 pieces colored in out of 12 pieces altogether that the square was broken up into. And sure enough, 6/12. What I really get is half of the square it's colored in as far as multiplying. I also really like some of these ideas for dividing. And so let's look at a couple ideas for division. Sorry about that. Shoot. Okay, let me bring this back up. Got a little too click happy on my X's.
Well, I think we all can understand.
Yeah.
We've all done that before, haven't we? Yeah, I really like the number line. I mean, that's just so powerful for students to be able to visualize, which way they need to go. And I like the idea too of the box as you're showing how to, deal with fractions and work with fractions. It's a great way to be able to visualize that.
So I just want to end on with fractions. We'll just end with kind of some division ideas, because I think students struggle like, oh, how do I divide fractions? That's harder to think about. And so again, I always go back to food, it seems like, because kids relate to that. And
Yeah, making us hungry.
of course, yeah. And so, students can, if you say, what is 12 divided by a half, a lot of times kids will say 6, because they think, oh yeah, half of 12 is 6. But then you have to help them think about, that's not really what we're doing, but we really are dividing. So let me bring this up to write on again. And basically what I'm saying is, what if we had 12 donuts like are in this box, and we really do divide them into halves? That's what we're saying. We're saying, how many times would a half go into 12? And if we really literally cut these donuts in halves like this, you can see, oh, what's going to happen is I'm going to start getting a lot more halves. I could actually serve more people now. Okay, instead of 12 people getting a whole donut, we could have 24 people each getting a half donut. So what is 12 divided by half? It's really 24. And that hopefully helps students start identifying the idea that what do we typically do with this is we change it to multiplying by the reciprocal. But why? Because that's what 12 times 2 is. That's another way to think of 24 is 12 times 2, and starts establishing not just, oh yeah, when you divide fractions, you keep, change, flip, or you always multiply by the reciprocal, but giving them kind of a why for why we're doing that. That fraction is going to go in there multiple times. It's really going to multiply instead of divide. Oh, and I did it again. So very sorry about that.
That's okay. It gives us some time to go grab a donut or something out of our
All right, sure, yeah.
As you're talking all about this food.
Okay, so then I'll move on from some fractions. I want to get into more because of some algebra type stuff that thinking about secondary, and there really are. I think as you move into the higher secondary grades, you're like, oh, there's no manipulatives I could use for that. But they're really, I have found as I teach algebra 2, there are some hands-on ways that you can begin to think about introducing some of the concepts, even like square roots and things like that. Kind of the last thing I have on here for fractions is kind of a fraction number line with kind of the bars or fraction strips that I developed. And so you see, kind of the bars, you can have students fill in what the different pieces are. And then the cool thing is, as they fill those in, they can kind of condense them down into one number line and see how those fractions compare to each other. It's also powerful if you look down the middle. Oh, you can see like 5/10 is the same as 4/8 is the same as 3/6. You see all the different representations of 1/2 that go together. And then you can begin to tie it into decimals and how the decimals play into that and how the percents play into that. So that's just another tool that I use when we're developing those connections. So for some more algebra type things, I thought we might think more about building kind of building functions as we really think about looking at linear patterns versus maybe an exponential pattern. And one of the things I've liked, and I got this activity from the current curriculum I use, it's called the College Preparatory Mathematics Curriculum, CPM. And it's just, like having students look at a pattern like, okay, what do you see at the beginning? What do you see happening? And so on. And this is basically the top is dots, and the bottom is these little tiles. But then on the bottom, what we can do is we can actually begin to color. Again, I like coloring like I was doing just a minute ago, because I think our brains respond to color well, and it helps us see kind of what's going on maybe a little better. So let me do this a little bit here. What I might do with this one then is, as the screens snip, I have students, okay, can you figure out, what the pattern is? And oftentimes they'll be able to say, oh, you're getting bigger by 4 every time, and that's great. But to help them really make that into an equation, what we might want them to be able to do is actually begin to color in some of these different little pieces. Sorry, this is getting kind of small. Let me click out of this. Let me redo this. Let's try this again. Okay, so as we look at this particular tile diagram, what I might do is color in, like I might draw the first tile and there was just one tile maybe to begin with. Over here, but then the idea was maybe every stage we kind of color the new tiles a certain color. So in that first stage, I'm going to color those yellow, and those are going to remain yellow the whole time. And the original one is going to stay maybe kind of white. Okay, and then the next stage, I might choose a different color. So those ones are going to be kind of a pinkish purple color going around there. Okay, so that represents the 4 that were added at the figure 3. And then you can begin looking at what was added the 3rd time. We might color those green. And you kind of begin building that, and that helps them if they really stop and think about what was going on in this pattern. They can really begin to think about, oh yeah, there was 1, then there was 1 plus 4, then there was 1 plus 4 plus 4, and they start seeing, oh yeah, it's just this repeated addition. And what do we use for repeated addition is multiplication. So hopefully they begin to build our equation. We're going to do this. That was the 1 original, the 4 yellow, the 4 purple, the 4 green, and so on. But how do we turn that into a general equation that could be for any figure number? Like if I want to go out to figure 100, then what we could do is just say, oh, it's 1 plus, and it's adding 4, but it's a certain number of times. We don't know how many times. And that makes sense then to bring a variable in and also multiplication. 4 times some number of times will be added. And we we could use that. The whole reason of coming up with an equation now is the other reason, kind of what Jacob was saying earlier, is it's not efficient to use little counters or coloring tiles to go estimate and draw what figure 100 is going to look like and how many tiles it's going to have. But now I could just use my equation to plug 100 in, and we can say that, oh, there's going to be 401 tiles in that next figure. So that's what I wanted to share about kind of building functions. Okay? And then the next one is a little bit the same way, but instead of a linear situation, be a little different. So this is about like a flu outbreak. Day 0, Velma and Stanley came back from their cruise, and they have this illness. Something's going on, and it's going to keep infecting this town. And the town is concerned about it. The town officials and everything. And so on this one, again, just something physical. I just had students use beans, like little pinto beans, to kind of count this out. And the beans are really helpful because what I've found students doing is they just jump straight to a table or to a graph. They start doing this, and as they read it, they say, oh yeah, each person's getting 2 people sick. So they start kind of doing things like this. They say, oh, there's 2 people sick when they fill this in. And then they say, oh, so now there's 2 more people sick, that double the number of sick people each day, and they just think it's doubling. But the problem with that is that doesn't count the people that are already still sick. So if we're counting everybody that's been infected, students kind of sometimes have a hard time, navigating that and seeing that. So a way we could kind of take care of that is, again, using something physical. I'll just use some little stick figures. But again, students might use beans or counters of some sort. And you can see, oh yeah, here's my 2 original people. And then here's the 2 people that each got 6. So we started with 2, and it actually went to 6 in the table. And then from here, each one is going to get 2 people sick, but not just the new group of people, also Stanley and Velma, the originals. So now if I went from 2 to 6, now what do I really see is I see 6 groups of 3, really, if I kind of circle them, there'd be 18 total people sick. And once the students kind of see that much of it, they start seeing the pattern. Okay, but again, even just starting with a physical thing for just a few stages of this, and even though they're not going to want to continue with the beans because it's going to get pretty tedious after that point to lay them all out and everything, they can start seeing, oh yeah, we start with 2 people sick, and then there's 6 total people sick, and 18. And if we stop and say, hey, what's the pattern? They can begin to say, oh, it's multiplying by 3. And then that helps us build, maybe make an equation and see this is not going to be linear. This is definitely going to be an exponential curve going something like this. You could build the equation a lot like we did previously, where we say, oh, it's 2 times 3, 2 times 3 times 3, 2 times 3 times 3, ... And then we begin saying, this is where we start moving to that symbolic idea of, is there a more efficient way to write this? Well, certainly. If it's a power of 2, or if it's 3 times 3, it's a power of 2, or second power, or third power, or fourth power, or whatever power we want to go up to. So we start using this idea of an exponential equation to represent that one. So then, of course, one of the biggest ideas in algebra is solving equations. Oh, I also put a link here. Just here's an example of what the beans might look like as students laid them out. the table on into kind of building the equation. So here's some counters, online counters that you could use to deal with that. So kind of as we move on, another big idea in algebra, of course, is solving equations and dealing with expressions and variables. And so I think this idea of an algebra tile, again, something physical that students can kind of get their hands on, can be helpful. So I use these little algebra tiles in my classroom. There's squares and rectangles and different things. And so this teal tile, we start introducing what these are. And I usually start with this very smallest one right here, and we start comparing it. And I'll actually go in and click in here. So I put a link there for an address that has the CPM tiles, but I'll just leave it on here for a second. So as we kind of establish what these tiles are, it helps students to kind of really unpack why we call them what we do. And that's really based on their area. This little dark blue one, we're going to call the 1 unit. And we call it 1 because it's just 1 unit by 1 unit. That's kind of a basic unit. Then we go over here to these teal ones, and it's 1 unit wide, just like that dark blue one is. And I'll say, well, how long is it? And students will start laying out some blue tiles along the side of it. And it's not exactly 3, and it's not exactly 4. It's somewhere in between. And so they say maybe 3.5. But I ask them, do they know exactly that it's that? And no, it's not perfectly anything. And so what we do is, what I say is, since we don't know exactly what it is, what if we just call it an x? And that would then make that as area. If we multiply to 1 times x, we're going to call that the x tile. And then I go over here and I say, oh, that also has an x dimension and an x dimension. It's x units across and x units tall. And what we end up getting there is an x squared unit. So then this just builds us this visual idea of, when I write down an x, when I write down an x squared, I can have a visual model that kind of pops in my brain about what that looks like. These other ones, basically, I could use a different variable now. I might call this y, and then this would be y squared. Okay, and so and then this one ends up being an x times a y. So as you go into more complicated expressions, you could use those. I just want to do a couple of simple expressions with the algebra tiles. So I'll just throw this picture up on the screen and say to students, okay, what do you see in this picture? Describe what you see. And some of them will say they see 3 x's and 12 ones. Okay. Other students will say they see 3 groups of something. Okay. 3 groups of x plus 4. And so those are both valid ways to think of it. Another way sometimes I'll do is I'll say, oh, could you take these? Could you arrange them in a rectangle? And they might come up with something like this. And then either way we want to think of this kind of leads us to using distributive property with students for expressions and with variables. Because they might naturally say there are 3 groups of x plus 4 here. And some people said that, and they saw that way, and they are exactly correct. There are 3 groups of that. But what else did other people see in the class? They might see that there are 3x plus 12, which again just says, oh, what's really happening is each piece on the inside is really getting multiplied by that number on the outside. We could also kind of take this and kind of look at this big rectangle now and kind of think more of a solid area model, that there are 3 rows, or this is 3 units high on the rectangle, and across the side it's x plus 4. And that might begin this idea of kind of rectangular multiplication of, oh, 3 times x plus 4 really will be a 3x and a 12, and seeing that the visual pieces of that rectangle being equal there. Those ideas with algebra tiles could be extended easily into dealing with when you have not just a single number on the outside to be distributed, but multiple. In elementary school, it might give students a picture like this and say, hey, how many dots are there? And they might begin to think about, oh, that first one looks 10 by 10, so that's like 100. That's easy to do. But then what we want to kind of help students see is, oh, this is really showing us what the result of a 10 plus 3 or 13 times 10 plus 2 or 12 would be. What would the result of 10 plus 3 times 10 plus 2 be, or 13 times 12? And you can see then, oh, there's going to be 4 different multiplications that have to happen: the 100, the 30, the 20, and the 6. And that kind of leads us to then maybe the idea of more symbolic, that's more easier to see, more visual because you can see all the dots. But what if we turn it like this? Oh, it's a plus b times c plus d. What are we going to do when we're multiplying binomials like this? Okay, and this is where I might, again, just attach maybe a little bit of a real life situation that they could visual. Like I've got a garden, it's x feet by x feet. Okay, and then I decide, oh, that's not big enough garden for me. It's only x squared units right now. That's kind of like my teal algebra tile from earlier. But I could just build basically, I want to add 4 feet in that direction. Maybe I want to add 4 feet in the other direction. And then I see, oh, I've got this new rectangle. Well, what is that rectangle made up of? I'll ask my students and say, can we figure out the area of that new rectangle? And of course, if we divide it and break it up into some littler pieces, and maybe even use our algebra tiles to represent it, they can begin to see, oh yeah, I can't just, as one of the common things that people want to do when they're multiplying, in this case, this is representing x plus 4 times x plus 3. Students will commonly just want to say, oh, it's got to be x plus 12. But if they're doing that, what they're getting is they're leaving out part of the multiplication. We see x squared here, we see 12 here, but is that the whole area of the garden? No, they're missing this whole rectangular part. Oops, wrong way. And they're missing this part. So they got a 3x and they got a 4x that they need to include in there. It's really a 7x, x squared plus 7x plus 12 for that visual multiplication. Okay, so we are getting close on time here. I've got more stuff that we're not going to be able to get through, and that's okay. It's always better to plan more, right? So when you get this presentation shared with you, you can go on and see some ideas for continuing that idea of multiplying the expressions out. And then I went into some ideas with some equations and just like equation balances. Again, a really visual way to do this for students. I even, again, give them things they can picture like grapes and watermelons. Back to the algebra tiles, I could actually use them and actually give them kind of a paper mat, and they could actually physically use the algebra tiles, especially when there's variables on both sides. It helps students to think, oh, I got to take an x away from one side and take an x away from the other side to see that I've got to keep it balanced. And as soon as I do that, oh, now I'm down to 2 x's over there, and that's easier. And so they kind of go through and they can basically try to get down to what one of these boxes would be equal to. One box must be equal to 3 as they solve it. So there's some other pictures, kind of ways to approach equations, some more algebra tile stuff. I'm going to click through. Some tape diagrams are really, I think, also helpful. These are some straightforward kind of multiplication ones, like 2x plus 12 equals 20, and how a student might solve down through that visually. But I also, sometimes we get some other equations that are harder to visualize. So I made this example up of just taking a brick of cheese, dividing it in 4 pieces first. And then Luigi really loved his cheese on his pizza, so he decided to add an extra bit to it. He decided to take that x over 4 and add 7 to it. And now he gets 12 pieces of cheese. And so from that, we could build an equation x over 4 plus 7 equals 12, and work backwards to solve what was the original size of the block of cheese originally before it was divided by 4. Okay, another tape diagram that we could think on this one, x plus 3 is this being divided into 5 pieces, and it's equaling 4. And so the equation we could then end up solving, which again, and these ones are sometimes hard to, I think, visualize or come up with an application for students to kind of picture or understand. But with this visual picture, hopefully they can see the x plus 3 here. Once it divided that same length into 5 smaller pieces, it was equal to 4. And their natural thing, the first thing they're going to probably say is, well, that bottom thing is equal to 20. And you're right, it is. And so that would help them see that, oh, the first thing you want to do in solving one like this is probably get rid of the dividing by 5. We want to probably multiply by 5 and see what that whole length would be, that it has to be 20. Beyond the equation stuff in this presentation, I had a visual substitution thing that's kind of fun that you might play around with, where you can basically substitute an apple's worth 3 bananas, and you substitute it, and students can figure out what a banana would be worth. And then I ended the presentation. I have a few geometry examples, like just discovering things about triangles. I just had students cut out a triangle. All of them cut out different triangles. And then we just tore off the corners of them. and then put them together, and they can see that, oh, there's a relationship here, that those corners, no matter what triangle that the students made, they're going to see that it's equal to 180 degrees, regardless of what triangle they made. Another thing, if you've not ever explored it, is really fun, is GeoGebra. GeoGebra has a lot of visual ways. So I don't think I have the link on here, sorry about that. But GeoGebra has some fun things. So on this one, you just slide it and it brings the angles together. And it has not just triangles, but it has, for different quadrilaterals, pentagons, hexagons, and so on. Okay, the last couple of things I'll go to. This next part was just about discovering congruent triangle shortcuts. And I actually physically cut out some little straws and angles and hand them to the students in a baggie. And we actually physically try to make these triangles. And I say, can anybody make a triangle out of these straws that's different than anybody else's? And they all have the same straws, a pink, a yellow, and a green. And when they put them together, there's only one triangle in the whole room. They're all the same as each other. So that brings up something like the side shortcut. And then I have some little angles cut out that are different colors. And I say, take the two straws and the blue angle, put them together. Can anybody make a different triangle? And they're all kind of forced to make the same triangle. So that's the congruent triangle piece. The last couple of things I really wanted to get down to share, so I'm going to skip a bunch of those things. Last thing I wanted to share was just a couple of things that I found helpful in my classroom in the last few years. Another area where I see my students struggling is just with word problems and trying to navigate through them and make sense of them. And sometimes I think it's just because we think they have more life experience than they do. Maybe we give them this word problem about, going and buying stuff with money, and maybe they don't have as much experience with that, or earning money at a job, and maybe they haven't had a job before. And so helping them pick out what's important in the problem, I call this the cubed strategy. And it's a way to kind of mark the text. It's kind of like in English or history, how people might pick out main ideas from an article they read or something like that. But in math, we're going to pick out kind of the main ideas or the main things we need from the word problem. So the C stands for circling the numbers, since most math problems are going to have some kind of numbers in them. The U is going to be for underlining any math terms. So underline math terms. And then the B is going to be to box the question. So whatever that's being asked to us, we're going to put a box around it, because that's what we're looking for. And especially in algebra, what is that going to end up being is probably our variable. So circle the numbers, underline math terms, box the question. And then the E is a little bit of a stretch, but it's X out extra information. Sometimes there's numbers in there that they're thrown at us, like a year that doesn't really matter or whatever. So you X that out. And then the last one is to define the variable. So that's not really marking the text, but once you've done those first 4 stages of marking the text, you can directly link into defining the variable. So an example, this week we were doing inequalities in my classroom. So I handed students each a little word card, and I wanted us to sort out what do these different words mean, and where would I attach these to as far as symbols? Are these an operation? Are these an inequality? What operation are they? What inequality are they? So they all kind of had them, and I said, okay, let's deal with anything that has to do with addition. And so students would bring up, and they put up their card. This is the scrambled version of it. And this is then what it kind of looked like once we got it up on the board, was with all the different symbols, with kind of their different vocabulary meanings. And so these would be, as far as math terms that I underline in a word problem, this is what I would encourage them to underline. And then as we tackled this next little example with cubed, I was able to just model for them how we could go through and circle the numbers and underline the math terms and pick out, what was really important. Because I think sometimes I give students a word problem, they just kind of stare at like, I don't know where to begin. So this gave them something to start with. Okay, so here's some money, here's some money, here's some money. Those are all important things. What are some math words we might talk about? Well, costs per week, plus per mile. Those are all kind of math words. Oh, here's one of the phrases that we had just talked about for inequalities: at most. And out of that, then they might after they underline, they might box the question. How far can he travel? Oh, that might lead us to defining my variable. Also, is there one of those numbers that doesn't really help me in my calculation or in my equation? I don't need to know that there's 3 friends. That's well and good, but it could be 4 friends or 10 friends. It doesn't really matter. But then I can say, oh, what is my variable? Maybe I want to, for how far we're traveling, I'll use miles, number of miles, or maybe D for distance. miles. And then I can start building my inequality. So just helping students have something to be able to kind of navigate through the word problem and help them pick out the important information. The last thing I'll just share is just a couple of quick strategies. Several years ago, I came across a series called Algebra with Pizzazz. And it had all these math problems with really, really dumb jokes that students would go through and do the problems, but they could check their answers by doing this little puzzle. And that was great. Sometimes the jokes were really dumb and I didn't like them, and students really didn't like them either. So then I got to thinking, well, could I do that same idea just in a practice sheet that I made up? Okay, and so this is an example for evaluating functions where I actually gave the students the problems, and then what I did off to the side is I just gave them all the answers, and I just call it scrambled answers. And as they go through the problems, as they get an answer, they can check if it's over there and cross it out. It's a little bit like when I was in school, we could maybe check our odd answers in the back of the book, and some textbooks had that still, and some textbooks don't. Sometimes we're not working from a textbook, but this is a way that students could check their work and be confident in what they're doing. And if they get the wrong answer and it's not there, they know they need to go back and figure out what their mistake was, and then I can go and help them troubleshoot it. The other thing you might notice on this top left is I gave them kind of a template of what I wanted to see for their work shown out and how they would show the steps out. And I found that, especially for my struggling learners, where they don't maybe know what to write or how to get started with it, they're a lot more, they're less reluctant to write out stuff if it's filling in the blank, at least at the first. And then when they get to the second one, they have a model to follow as they're going back and doing that. So that's just an idea of scrambled answers and work templates. This is another one with like midpoint and distance formula with the same thing. I had a couple where I had them have the template, but then I kind of graduated them away from that and kind of weaned them away from it so that they could do it on their own. And then I had scrambled answers on both sides of that sheet for them to check their work. And then the last one is kind of a review game thing that I'll often do depending on what the questions are or the kind of the situation is, but I call it problems for points. And so this week in one of my classes, I gave them these 4 problems about exponential growth, and they had to come up with an equation and solve it and use their calculators to figure out what the new values would be. So I just had these 4 different colors of cards on the back table. I had maybe 4 or 5 of each color on the back table, and it was kind of like a relay. So they would be in groups of 2 or 3 in teams. And then I would just say, okay, ready, set, go. They would go back, grab one card, take it back with their team, and on their little mini whiteboards in class, they were working them out and calculating and collaborating. It was really, really great to hear them talk about them and work through them. And when they had an answer, they would come and show me, and I would check it with my key. And if they had the right answer, then they would get 6 points if they were the first group to get that thing. So these are just sticky notes I laminated. I put magnets on the back of them and put them on my board. And so if they were the first group to get that problem, the pink problem or the A problem, then they took 6 points back to their team. If the next group that got that one right would get 5 points and on down to 2 points or 1 point. And then each color corresponded to one of the problems. And they don't have to start with A, B, C, or D. They could start with any one they wanted to, pick a problem, grab it, solve it, and come and get some points for solving it. And it's just kind of fun. Students enjoy it. They get a little competitive with it. They're working through it, trying to get the answers, and in the end, we total up the number of points they got, and they've usually had a good time doing some math. So that's with 4 problems. You could do it with 8 problems. This was a systems of equations one I did, and they had to kind of decide what method was going to be best. Is substitution best? Is graphing best? Is elimination or the addition method best? And so that had 8. So I had a bunch more sticky notes, different colors, but anyway, so they could get all their points for those. And of course, this one took a little longer. The more problems you have, the longer it's going to take. So I have several times where I just use 6 problems instead. So 4 problems, 6 problems, 8 problems, any of those work well. So those are just some ideas that I've had that I wanted to share with you that have worked well in my classroom in the last several years. And with that, we'll see if there's any questions and wrap it up.
Dr. Ray, are you? Yeah.
Yeah, what a fascinating presentation. I'm amazed by it, Cary. Thank you so much. Before I turn it over to questions, I just want to give you one short word of wisdom that I ran across that I thought would be very appropriate for today's workshop. And it is this: most of my work as a math teacher isn't even math. it's helping students believe that they can also do math. And Cary, you've given us some wonderful ideas on how that can happen, and thank you so much. Dr. Jake, I have another meeting that I need to go to, so I'm going to let you finish this up. And thank you all for attending today. And Dr. Jake will give you the instructions and take questions at this time. Thank you.
Yeah, thanks, Dr. Ray, and have a good rest of your day and weekend. And so what I've posted in the chat is the survey. Please make sure you fill it out in its entirety. You need to make sure that you post in there what you did learn, because Mr. Cary went over a lot of different information and talk about some ways that you can implement some of these strategies into your classroom. And so with that, we'll stay on for an extra 10 minutes while everyone is getting on and filling out the survey form. It's for those that are on our Facebook live feed. It's also in the chat on our Facebook feed, and then those that are on Zoom, it's in the chat also. So if you have a question, you can raise your hand or throw the question into the chat. Anything about mathematics, because Mr. Cary went over a lot of different information here, a lot of different ideas that you can implement. I think the big thing, Mr. Cary, was about the very beginning, how kids learn how to manipulate the items, and then they move on to something a little bit more abstract where they look at the different drawings of items, and then they actually get into more abstract with using X's and Y's and everything else like that. Do you find that sometimes you have to go back in junior high and use manipulatives to help them visualize it a little bit better?
Yeah, I do. I have like 3 or 4 classes of on grade level kids, but I've typically also had one class that's directed primarily at kids that were struggling learners. And so especially with that group, I found going back and using the manipulatives and the pictures, the visual pictures, that group, it really, really helps a great deal.
Yeah, that's good. And a couple questions in the chat. How do you evaluate your students? What are some good assessment tools that you utilize?
So I mean, I do kind of regular paper tests a lot, but even in, that's more the summative type assessments, but just even in class, one of the great ways just for quick feedback from students, check for understanding, is whiteboards. So I'll have them doing problems out on whiteboards, hold them up, and I can see an answer very quickly. Another one I've just discovered last year, and I don't know why I didn't think about this earlier, but like as we're solving a problem, a lot of times I'll say, when you get the answer, will you just show me the answer on your fingers? And of course, that only works if it's whole number answers and stuff, but a lot of times our answers are whole numbers. And so sure enough, they'll hold up 2 fingers and I can see very quickly, oh, yep, you got it. And it's just a really quick way to get feedback, and also gets them a little actively participating in responding, and they don't have to say their answer out loud necessarily. So it works really well for students who don't like to answer, but they can give me that feedback very quickly.
That's great. What about whiteboards? Do you use whiteboards for that?
Oh yeah,
quick assessment?
Yeah, the mini whiteboards. Yeah, I'll use those a lot. Students love writing on those.
Yeah. Do you ever do exit tickets? So students write on a sticky note or a little 3x5 card as they're leaving. You can give them a problem they have to work on, so the next day you know what to focus on.
Yeah, absolutely. Yeah,
that's great.
Those are good.
What about there's another question from Riham. Are there any interactive platforms for math or websites or games that you recommend? I know there are a ton out there, but I think they're asking, like, what are some of the best ones that you utilize?
I mean, some of those ones that were in the PowerPoint, that IDAX has some rich virtual manipulatives. A while back, there was one called the National Library of Virtual Manipulatives, and I really liked it. It's out of University of Utah. But the problem they ran into was their stuff, their visual was all outdated and didn't transfer very over to the new kind of visual stuff that was on the computer and stuff. So that one doesn't work as well anymore.
Yeah. I know there's a lot of different ones, but I think we have to be careful that some are just games that students aren't really learning anything. It's just keeping them occupied and using it as a babysitting tool. We don't want to do that.
Right, but I guess the other two that I would mention is Desmos. Of course, Desmos online graphing calculator has a lot of rich activities and easy to manipulate graphs to make. But then GeoGebra that I mentioned earlier it has a lot of interactive things that people have already built. You can just go in and search, sum of angle of triangles, and you can find all kinds of different demonstrations that you can easily do for students. So.
What I liked in throughout your presentation, you talked about different tools that could be utilized, but they were under the direction of a teacher, it seemed.
As far as the manipulatives or the you can, and that's the thing, you can do it both ways. Like you can distribute the stuff out, and there are times where I like to have it in their hands, but there are times where I don't want to hand up all the number chips. But once we've established that kind of relationship, just put them up on the pictures on the screen, and they can kind of see it also. So
yeah.
Some of that depends on time in class and stuff.
Absolutely, yeah. Well, Delphine has a statement or question. Why do learners find math to be very hard? And this is a age-old issue, I know.
Oh, yeah. I don't know why students get that stigma. I just know that if they can have a good experience for the year in my classroom, that can make such a difference for them. And so I just try to make it fun. I try to make it intuitive, where it's not just, like, oh, you got the wrong answer, you're wrong, or that kind of idea, but helping them really say, oh, okay, so it's not right. Why isn't it right? And really more of a thoughtful way of saying, how can we go back and see why it's not, understand the whys of it, I guess. And the class I think of right now that I have like 15 students in there that typically have been struggling learners. And throughout the year this year, I've just heard things like, oh, I've never done that well on a math test, or, oh, I really get this now. And that's really rewarding to me when I hear that.
Yeah, because sometimes that's all that it takes is students to have a little bit of time where they can build some of that confidence up. Because I think a lot of kids are missing that confidence.
And what Ray shared earlier, convincing them that they can do it. But showing them that you believe in them, that they can.
Right.
And even if they make a mistake, it's okay. We're all going to make mistakes. And so you move on from that, and you just keep learning and keep trying and keep building and keep growing. So.
And I bet you could do an amazing workshop just on that, allowing students to struggle, overcome that struggle, and then see the change in the confidence that they have in working with mathematics. But that can be applied to any subject area.
Yep.
Love it. Last question. Do you think homework is good, or it might be overwhelming?
I think in math, practice is absolutely important. I equate it to music or sports. And I'm like, if you don't practice, come game time, come recital time, you are not going to be prepared. And so kids need to practice. Now, do they have to have 100 problems of practice? No. Can you give them a reasonable amount of practice? I think so. And like I was showing earlier, you can make it less overwhelming if you give them some help, like the little template to fill in, so they kind of understand what you want, and like those scrambled answers, because then they have that confidence knowing, yep, I got that answer. I got all my scrambled answers to match up, so I feel confident that I've done this right. And that way they're also not practicing it the wrong way. If they made a mistake, they go back and fix it, and like, oh, now I know how to practice it the right way. So I do think there's absolute value in independent practice. How that plays out in your classroom, whether that's more class time work or actually take homework, that depends a lot on different situations, different students, and your schools. But I do think practice is important.
Yeah, especially if they make sure that they do it the right way, and that it's just not wasted time, that it's not repetitive of doing 100 problems. You're right. I think that's a common issue that we have, not just in math, but in a lot of other things too, to find that balance, to ingrain it in the students, but not to, overwhelm them. So,
or bore them, right?
Right. Yeah. Well, thank you, Mr. Cary Hill. We appreciate it. Appreciate everyone coming into this workshop today. It looks like a lot of the surveys have been completed. If you have questions, or if Array Global can support you in any way or any time, please feel free to reach out to us. You'll receive your certificate this coming week. And along with that, we will include a link for the PowerPoint, because there are a lot of questions for that PowerPoint. So we appreciate that. And then those of you who are in Jeddah or in Yerevan, Armenia, we will be in those countries starting on Saturday, on the 20th. So please reach out to us. We'd love to meet with you. We have some workshops that will be taking place that you can learn more about on our website and our Facebook page. And we will see you all there. And thanks again, Mr. Cary. Appreciate that. And
Thank you all for being
Have to have you
here and
back.
for your nice, kind comments in the chat too.
Yes.
Appreciate it.
Excellent. Thank you. And everyone have a great evening or great day wherever you're at.
All right, and I'll send you the link there for the PowerPoint. Okay.
Excellent. Thank you.
Thank you.
Yep. Bye.